first modulation type is a very simple one. It's the amplitude modulation. As I have already pointed out in the previous video, we have a carrier here printed in blue, and then there is the information here printed in red, which is also a sinusoidal signal in this case, but it can be some other signal too, but we'll use a sinusoidal signal here just to as an example to visualize the modulation. And what is done here is that the amplitude of the carrier is just altered, and it follows the information. Yeah, so you see here the information dotted in brown, and as the envelope of the modulated carrier. And mathematically, this amplitude modulation is just a multiplication of the carrier and here is our information. This is the modulation index, and it is used to control the amplitude here of the envelope. So a higher modulation index would, for example, lead to a higher envelope. Yeah. And what does it look like in the frequency domain? So you will find all the mathematical derivations of all relations between time domain and frequency domain in the lecture notes. So please refer to the lecture notes for more information and for background information. In the frequency domain, our multiplication becomes a convolution. So you will find a multiplication in the time domain, and this becomes a convolution in the frequency domain. And what does it mean for our signal? So we have the information here. This is the information, and it is distributed here in a band around 0, and this band is called baseband. We won't use the term baseband here too much, but we will come back to this later when we speak about mixing. And yeah, this information can be, for example, our spoken voice, and the baseband is then limited by 20 kilohertz, for example. And now in the time domain, this information is multiplied by the carrier signal, and in the frequency domain, this means it is convoluted. And this convolution leads to a frequency shift. So the baseband is shifted by the positive part of the carrier to the radio frequency band. So radio frequency, or in short RF band. And this can be, for example, our 144.3 megahertz. Yeah, and remember that the carrier is usually a real valued signal, so it does exist physically. So it is real valued because we cannot have complex valued signals in real life. So for example, as a voltage signal, so all voltage signals are always real valued, and therefore we have an even symmetric Fourier transform of our carrier signal, and this is the negative part here. And this negative part leads to a shift also in the negative half plane of our frequency domain, so that our RF band is again symmetric. So we have a positive part and a negative part, and our transmitted signal is therefore real valued because it fulfills the symmetry rules. And we can put the voltage signal, the voltage RF signal, onto antenna where it is radiated into the air. The transmission has a certain bandwidth, 2, which is the transmission bandwidth. Here in this case for the amplitude modulation, it is approximately the baseband bandwidth, but depending on the modulation, the transmission bandwidth can be different. And there's a special property of the amplitude modulation. It is shown here. Let's change the color here and here too. So the carrier is transmitted. Let's go back to the slide here. You still see the carrier here in the time domain. The carrier is still present, although its amplitude changes over time. And in fact, the transmitted carrier also requires energy, so the total signal power is composed of the information, which is shifted up to the RF band, so the modulated information, plus the carrier, which is still present. And the let's call the problem is that the carrier does not carry the information itself, so the information is located here in the sidebands around the carrier, but here the carrier itself does not contain any information. It just consumes signal power. The power has to be radiated into the air, and but it is actually not useful to carry information. And so the idea is to suppress the carrier, and this is the modulation which we will have a look at in the next video.